NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will master a reliable algorithm for solving equations of the form log base a of f of x equals log base a of g of x. We'll visualize each rule and then apply it to a concrete example. Step 1. State the equation and remember the base conditions. The base a must be positive and not equal to 1. Step 2. Convert the equation into an equivalent system using the argument of the left logarithm. We require f of x to be greater than 0, and we set f of x equal to g of x. Step 3. Alternatively, use the argument of the right logarithm. Require g of x greater than 0, and again set f of x equal to g of x. The two systems are equivalent. Choose whichever inequality is simpler to analyze. We start with log base 2 of x squared minus 4x plus 3 equals log base 2 of 3x plus 21. This equation is equivalent to the following system. 3x plus 21 is greater than 0, which means x greater than -7, and x squared minus 4x plus 3 equals 3x plus 21. Now move all terms to one side. We get x squared minus 7x minus 18 equals 0. Factor the quadratic. That becomes x plus 2 times x minus 9 equals 0. So the candidate solutions are x equals -2 and x equals 9. Check against the domain x greater than -7. On the number line, both -2 and 9 satisfy the domain. Therefore, the solution set is curly bracket -2, 9 curly bracket. Problem 2. Log base 1/10 of the fraction 2x squared minus 54 over x plus 3 equals log base 1/10 of x minus 4. This is equivalent to the system x minus 4 is greater than 0, that is x greater than 4, and the fraction equals x minus 4. Rewrite the equality line to work on it. 2x squared minus 54 over x plus 3 equals x minus 4. Multiply both sides by x plus 3 to clear the denominator. That gives left parenthesis x minus 4 right parenthesis times left parenthesis x plus 3 right parenthesis equals 2x squared minus 54. Expand the left side and bring all terms to one side. We get x squared minus x minus 12 equals 2x squared minus 54. Moving terms gives x squared plus x minus 42 equals 0. Factor the quadratic. That becomes left parenthesis x minus 6 right parenthesis times left parenthesis x plus 7 right parenthesis equals 0. So x equals 6 or x equals -7. Finally, check the domain x greater than 4. Only x equals 6 lies in the allowed region. -7 is rejected. The solution set is curly bracket 6 curly bracket. Here is the problem. We must solve the equation open parenthesis log base 5 of the square root of x close parenthesis squared minus log base x of 5 times the square root of 5 plus 1.25 equals 0. The domain is x greater than 0 and x not equal to 1. Step 1. Rewrite radicals as exponents. The square root of x is x to the 1/2. Also, 5 times the square root of 5 equals 5 to the 3/2. Step 2. Use the power rule for logarithms. Log base b of a to the p equals p times log base b of a. Because of the square, 1/2 times 1/2 becomes 1/4. The exponent 3/2 comes out in front. Step 3. Combine the product of identical factors into a square. Step 4. Apply the change of base formula. Log base x of 5 equals 1 over log base 5 of x. Introduce the substitution t equals log base 5 of x. Introduce the substitution t equals log base 5 of x. Step 5. Substitute t for log base 5 of x. Step 6. Replace 1.25 with 5/4 and multiply the equation by 4t to clear denominators. This yields a cubic equation. Step 7. Rearrange to prepare for factoring by grouping. Step 8. Factor the difference of cubes, t cubed minus 1, as t minus 1 times t squared plus t plus 1. Keep the 5 times t minus 1 term. Step 9. Factor out the common factor t minus 1. Step 10. Apply the zero product property. Either t minus 1 equals 0 or t squared plus t plus 6 equals 0. The quadratic has negative discriminant and gives no real roots, so the real solution is t equals 1. Step 11. Back substitute t equals log. The quadratic has negative discriminant and gives no real roots, so the real solution is t equals 1. Step 11. Back substitute t equals log base 5 of x. Step 12. Convert from logarithmic to exponential form. 5 to the first equals x. Therefore, x equals 5. Finally, we write the solution set and confirm it fits the domain conditions. Log of x equals 1/2 times log of x plus 1. Therefore, multiply both sides by 2. 2 log x equals log of x plus 1. Apply the power rule. Log of x squared equals log of x plus 1. This equality of logarithms is equivalent to the system x greater than 0 and x squared equals x plus 1. Rearrange to the standard quadratic x squared minus x minus 1 equals 0. Solve to get x equals 1 plus square root 5 over 2 and 1 minus square root 5 over 2. Check the domain x greater than 0. Only the positive root survives. So the solution set is the singleton with x equals the golden ratio, 1 plus square root 5 over 2. Now we move to equation 2. Equation 2. Log of 8 minus 10x minus 12x squared equals 3 times log of 2x minus 1. Use the power rule. Log of 8 minus 10x minus 12x squared equals log of 2x minus 1, quantity cubed. Equality of logs gives the system 2x minus 1 greater than 0, which means x greater than 1/2, and 8 minus 10x minus 12x squared equals the cube of 2x minus 1. Expand the cube on the right to 8x cubed minus 12x squared plus 6x minus 1. Collect terms to obtain 8x cubed plus 16x minus 9 equals 0. Factor 2x minus 1 times 4x squared plus 2x plus 9 equals 0. This yields x equal to 1/2, while the quadratic factor has no real roots. Finally, apply the strict domain x greater than 1/2. The root x equals 1/2 is not allowed. Therefore, there is no real solution to the second equation. Recap. For equation 1, the valid solution is x equals 1 plus square root 5 over 2. For equation 2, the only algebraic root is 1/2, but it fails the domain x greater than 1/2, so there is no solution. In this lesson, we will solve the trigonometric logarithmic equation step by step. The problem is, log squared of cosine x equals log of 1 minus sine x times log of 1 plus sine x. Step 1. Establish the domain. Each logarithm requires a positive argument, so cosine of x must be positive. Also, 1 minus sine x must be greater than 0, and 1 plus sine x must be greater than 0. Putting this together, cosine positive restricts x to intervals centered at even multiples of pi, with width pi. Step 2. Introduce a clean algebraic view. Let u be log of 1 minus sine x, and v be log of 1 plus sine x. Notice that u plus v equals 2 times log of cosine x, because the product of 1 minus sine x and 1 plus sine x equals cosine squared x. Step 3. Rewrite the original equation in terms of u and v. We started with log squared of cosine x equals u times v. Since u plus v equals 2 log cosine x, the left side becomes 1/4 times the square of u plus v. Setting 1/4 times the square of u plus v equal to uv gives a perfect square. U minus v quantity squared equals 0. Therefore, u equals v. Step 4. Translate u equals v back to x. Logarithm is 1-to-1 on positive numbers, so u equals v implies 1 minus sine x equals 1 plus sine x. That yields sine x equals 0. Hence x equals k times pi. But remember the domain. Cosine x must be positive, which keeps only the even multiples of pi. So the solution is x equals 2k pi for any integer k. Visually, cosine is positive to the right of each even multiple of pi, and up to 1/2 pi away. That includes the points 2k pi where sine is 0 and cosine equals 1. Final answer. The complete solution set is x equals 2k pi for any integer k. In this example, we will find all values of a for which the equation log of ax equals 2 times log of x plus 1 has exactly one unique solution. Step 1 is domain. For logarithms to be defined, their arguments must be positive. That gives us ax greater than 0, and x plus 1 greater than 0. Next, use log rules. 2 times log of x plus 1 equals log of x plus 1 squared. Since log a equals log b implies a equals b in a common base, we get ax equals the quantity x plus 1 squared. Expanding, that gives x squared plus quantity 2 minus a times x plus 1 equals 0. For the quadratic to have real roots, we need the discriminant at least 0. The discriminant is the square of 2 minus a minus 4, which simplifies to a squared minus 4a, so is less than or equal to 0 or is greater than or equal to 4. Note that when it equals 0, the domain condition ax greater than 0 fails for all x, so a equals 0 is excluded. Let's write the two roots explicitly and also record Vieta's relations. The sum equals a minus 2 and the product equals 1. Now analyze cases to guarantee exactly one valid solution of the original log equation. Case 1, a less than 0. Here, the sum of minus 2 is negative and the product is 1. So both quadratic roots are negative. Check the domain x plus 1 greater than 0. Compute x1 plus 1 and x2 plus 1. We find x1 plus 1 greater than 0, but x2 plus 1 less than 0. Also, since it is negative and the valid root x1 is negative, a times x1 is positive. Therefore, for a less than 0, exactly one root satisfies both domain conditions, so the original equation has exactly one solution. Case 2, a greater than 4. The sum of minus 2 is larger than 2, and the product is 1, so both roots are positive. That makes x plus 1 greater than 0, and a x greater than 0 for both roots, hence two valid solutions. This case does not give exactly one solution. Case 3, equals 4. The discriminant becomes 0, and the quadratic is x squared minus 2x plus 1, which is the square of x minus 1, giving a single root x equals 1. The domain holds since 4 times 1 is positive and 1 plus 1 is positive. Therefore, at equals 4 yields exactly one solution. Final answer. The equation has exactly one unique solution when it is less than 0 or when it equals 4. Example. We'll rewrite it clearly on screen in bold orange latex. Step 1. Replace the constant 1 by log 10 and combine the left side using the quotient rule. Since log 10 minus log 5 equals log of 10 over 5, that is log 2, we will show the quotient rule card first. Then we write log 2 equals 1/3 times the bracket of negative log 2 plus log x plus 1/3 log 5. Step 2. Multiply both sides by 3 to remove the 1/3. Step 3. Move the negative log 2 to the left and collect like terms. Step 4. Use the power rule to send coefficients into exponents. Power rule card. Step 5. Combine the difference of logs as one log of a quotient. Step 6. Since the logarithms are equal, their positive arguments are equal. Therefore, x equals 16 divided by the cube root of 5. Divided by the cube root of 5. In this example, we will solve a logarithmic equation following a clear, step-by-step structure with domain checks and algebraic rules. Step 0. Determine the domain. All logarithm arguments must be positive, and the square root requires a non-negative radicand. So we write three inequalities x minus 3 greater than 0, x plus 5 greater than 0, and 2x plus 1 greater than 0. The intersection gives x greater than 3. Step 1. Multiply the entire equation by 2 to clear the 1/2 factors. Step 2. Apply the power rule for logarithms. C log base b of a equals log base b of a to the power c. Move the coefficient 2 into the exponent. Step 3. Simplify. The square of the square root gives x minus 3. Step 4. Use the product rule. Log base b of a plus log base b of b equals log base b of a times b. Combine the two logarithms on the left. Step 5. Because logarithm base 5 is 1 to 1, we can equate the arguments. Step 6. Expand the product and move all terms to the left to form a quadratic. X squared plus 2x minus 15 equals 2x plus 1, which simplifies to x squared minus 16 equals 0. Step 7. Add 16 to both sides to get x squared equals 16. Then take square roots to get x equals plus or minus 4. Step 8. Check the candidate solutions against the domain x greater than 3. -4 is rejected. 4 is valid. Therefore, the solution set is the single value 4. Recap. We found the domain, applied the power and product rules for logarithms, used the one-to-one property, solved the resulting quadratic, and kept only the value that satisfies the domain. Final answer x equals 4. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.